Welcome everyone back with Fun with WebGL 2.0. In today's lesson, we start to have some fun. Today we're going to build our first camera. Before we start looking at some code, there's 3 points into how a camera works that we kind of need to discuss a little bit. The first thing we need to realize that is our viewport exists in a 1 unit big cube. Anything past 1 unit at any direction from origin is not viewable. That's pretty much our whole virtual world. That's how big the actual world is. It's a really small room that we live in WebGL. Which leads us to point 2. To make our world look infinite, we have to use something called a projection matrix. If you were used to using 3D modeling tools, you would know them as perspective mode and orthographic mode. So we're going to set up a projection matrix using perspective. This allows us to make our 1 unit space look near infinite. And when I say near infinite is that we give it a range of how far we can see it. So in matrix 4 object, we have an equation that sets up our perspective. And we give it our field of view, the ratio of our canvas, how far we can see, and how near we can see. And those are the 4 parameters we need to set up, and it creates a nice transformation matrix for us that we can then pass into a shader that will then warp our vertices to give the illusion of depth and distance. And now we're going to move on to the final point. Just like in Portals, where the cake is a lie, so are cameras. Cameras are a lie. They do not exist. If you're coming from any gaming engines like Unity, Unreal, or 3D modeling tools like Blender, you're used to seeing a camera as an object you can move around, you can rotate it to the angle that you need, and it kind of just magically gives you a viewport of the direction the camera's looking at it. Because we kind of have an understanding of what a camera is, because you have a phone, you have an actual camera, and when you take photos, you move yourself around to change your perspective and your point of view. So when you think of a camera, you think of something that you control and you move around, and you change your own perspective to change what you're actually looking at. That's not how cameras work in virtual reality. Cameras are a lie. They're not something physical. They're not something you actually move around. The world isn't static and the camera moves. It's the exact opposite. A camera is just another transformation matrix. And to make the camera work is that you actually get the inverse of the matrix. So the idea is that in the real truth of it all is that you as the viewer have a fixed point in space. You can't turn around, you can't do nothing. And the camera is just the inverse of what you expect to happen. So if you want to take 5 steps back, what you're looking at in front of you looks like it's taking 5 steps forward. That is an inverse. You're taking 5 steps back and it's really going 5 steps forward. So that's what the inverse transformation is. So if we set up our camera 5 steps back, which is a +5, and we do an inverse, it becomes -5. And then we apply that -5 transformation on all our vertices, which then pushes the vertices away. It gives the illusion that we're walking backwards, but we're not. It's actually the world is moving forward. And that's the magic of how cameras actually work. You, as the viewer, exist at a fixed point. It's the entire virtual world that moves for you. It rotates, it translates, it scales, it does all this around you, and the projection matrix with the camera matrix is what gives the illusion that everything is traversable, that you can move around, you can crawl, you can look up, you can look down. It's all an illusion. And that is the magic of cameras. Cameras, like I said, are a lie. They don't function as you expect them to. They just give you a way to move the world around to create the point of view that you expect to see. So now that I'm finished my long spiel about how cameras work, let's look at some code. So here we have our new file called camera.js file. After that long explanation, hopefully the code now will start making some sense. So in our constructor, the first 3 lines of code that we're going to do is just set up our projection matrix. Remember, this is what allows us to create distance and depth. What makes a cube go from a square to an actual 3-dimensional cube when we look at it and when we rotate it. After that, we set up our transformation, which is the same transform object from the previous lesson that we apply to models. And then, of course, we have a view matrix that we're setting up in our camera that's independent of our transform view matrix. This one is the one we're going to cache the inverse. And then the last thing in our constructor, we're going to set up modes. We're going to have 2 separate modes in our camera. We're going to have the ability to orbit, which the camera just rotates around the origin, or in all honesty, the whole world just rotates in front of you. And we're going to have free mode, which is basically a first-person camera, where you are able to move forward, back, left, right, turn around, just like any first-person shooter game. So that's pretty much the gist of the constructor, And like I said before, in our perspective, we have some defaults set up already. On line 6, we have the field of view. It's at 45 degrees. The ratio is just a ratio between the width and height of our canvas, which comes from our GL object. Near is the minimum distance that's viewable. So if something is at a z-axis of, like, say, 0.005, we won't be able to see it. It has to be at least at a minimum of 0.1. And we can see as far as 100 units away. You can actually set up whatever numbers you want, but these are the defaults. But when you initiate the camera, you can set up any additional parameters, or you can change the parameters how you see fit. If you want to increase the distance or decrease it, or change the field of view just to see what things look like. After the constructor, we have 3 panning functions. And panning is moving based on the direction you're looking at. So if you're used to playing video games, it's like strafing left and right. No, you're still viewing forward, but you can strafe to the left, strafe to the right. That's basically what our pan X would be. Pan Z is basically our forward movement based on our direction. There's 2 different types of forward movement you can deal with. You can do, like, if you're making a space game, you move forward based on the direction you're looking at. So because all 360 degrees of any angle you can move around in. If you're working in a game or like a first-person character moving around, you're not really moving at exactly the direction that you're looking at. You're looking at just the forward direction of just regular Z. Like, you just change the Z position itself. You don't actually change X, Y, Z based on rotation. That's really what panning kind of does. It just, based on the rotation, it then moves in that specific direction. And our panning modes will work slightly differently depending what mode you're in. So each direction functions differently. And if we scroll down, we'll see that we have an update view matrix function. This one replaces the one that's in our transform, because the camera doesn't need to do as many things as the actual normal transform does. Like, one thing is the cameras don't scale. They should not scale. That's what our perspective matrix is doing, because if we're moving things far away from us, it's actually scaling it down. It's making things look far away by making it smaller. So that matrix is what really handles our scaling. So our camera itself shouldn't really handle scaling at all. So this function kind of just removes it and changes the order based on the mode. So if we're dealing with a free mode, we're going to translate before we rotate. And if we're going to do the orbit, we're going to rotate and then we translate. And then after we figure out how we're going to set up our transformation order, we call its update direction function. So this way we can get the direction all set up and ready to go. We need to know the direction for panning. So that's the reason why we're getting our directions set up after the transformation is all updated. Now we take our transformation matrix and do an inverse on it, and then save that matrix in the camera's view matrix, and we return that. And then you see at the very bottom we have our constants that sets up the mode, which is free in orbit. And that's our camera object in a nutshell. This object pretty much just handles the state of our camera, all the transformation information. And now if we scroll down a little bit more, our state is going to be controlled by our camera controller object. I'm pretty much not going to bother explaining too much of this object because this is all just regular JavaScript stuff, very simple, regular programming. Just all it does is just handles mouse events, and based on the mouse events, it performs the action we expect it to. We use the scroll wheel to zoom in and out, and then we use the mouse hold down and drag to rotate around. And if we hold down the shift key while we're dragging, it does a panning instead of rotating. That's all this object does, is it's just it gives us a mouse control over the state of our camera. Now with all our camera stuff all set up and ready to go, let's go back to our view.html page. At the top, we're going to add our new JS file. Then we're going to start fixing up some of our load events. And we're going to, before we even do the load events, we got to add some new global variables. So at the very top where the var global variables exist, we're going to add gcamera and gcamera controller. Now back in our load events, that's what we kind of just set it up. We're setting up our camera. We're just passing in our GL context. We're not going to bother filling out the rest of the parameters. The default perspective will work just fine. And then we kind of move the camera in position. We're changing its Y position. We're moving the camera up a little bit, and we're moving it back 3 steps. And then we set up our controller, and we pass in our GL context plus our camera object. The next thing we do is pass in our perspective to our shader. And before we do that, we kind of have to activate it. This is kind of sloppy, but we're going to change this by the end and make it more friendly. But for now, we're just going to activate, set the perspective, and then deactivate the shader again. And then we go to our on render. We get rid of everything we had before and replace it with what we have. We're going to update our view matrix for our camera. We're going to clear the canvas. We're going to activate our shader. We're going to push in our camera view matrix, which is the inverse. And then we just start rendering our model, which is our grid. Now we move down to our vertex shader. In our vertex shader, we're going to add our projection matrix and our camera matrix. And then we're going to apply those transformations to our position. And we have to apply them in a specific order. So the order would be projection, camera, model view, then our actual vertex position. You can try changing the order and things might not function the way you expect them to. But they have to be in this specific order to make things render the way you expect them to render. Now, if everything's done right and you go back to the browser, you should be able to start rotating and panning the grid. Now, you should now actually start working. Your camera is not working, and now you're starting to have some control over your 3D world. So now with that out of the way, now let's go back into our primitives.js file to start modifying a couple of things. One of the first things we're going to do is add a create model static function, which just creates a model and our mesh at the same time. It just so we can get everything built in with one line of code. And then you kind of see I highlighted a lot of the other changes. And one of the changes we're going to do is just swap all our Y positions for Z positions. We're going to start building the grid on the floor, not in front of our view. And we're going to change all the color references to the index 0, which would be the gray color. Then as we move back to our browser and refresh, we'll see that our grid is now on the floor. And because of our camera and our projection, we actually can see it as an actual floor that you would normally see in a 3D modeling tool. But still, we got those test lines in there from the previous lesson. So let's get rid of those those two lines, and let's add in actual lines for to point at our axis. So going back to our prisms.js file, we're going to add an include axis parameter for both of our static functions. So this way, the axis can be an option that we could turn on and off. And near the bottom at line 39, we have a to-do that from the previous lesson that's kind of marked that the following code is just temporary. So let's get rid of all these lines of code, or you can just tweak them and copy and paste them into this new code. And it's surrounding our if statement, so we can turn this on and off at the very end of our algorithm. And all this does is just create 3 lines for each axis that we want to display, and each axis gets a color. So X, Y, Z will get red, green, blue. Then the only thing left to do is to go back to our HTML page and enable this new parameter. Now if we move on to our browser and refresh and start rotating around, you'll see that now we have the floor and 3 lines that will tell us what our axes look like and how far they go. But looking at this, the world looks a little small for us. So let's go and open up our jl.js file. Now if we scroll to the bottom after our set size function, we're going to create a new function, and we're going to call it fit screen. This new function is going to take in 2 parameters, which would be a percentage, and it'll be just any number between 0 and 1, and it will give us a percentage of the actual total size of our browser viewport. So this way we can fit as much as we want on a screen. And before we go modify our HTML page, let's create a new file called shaders_extras.js. In this file, we're going to extend the shader again and create a shader called grid axis shader. So we're going to take the code that it currently exists in our test shader stuff on the HTML page, but we're actually going to hard code it into this class because we're pretty much done with that shader and we want to keep this for future use. So at this point, we could just hard code in all that shader source code right into our class. And just like I said, the base class automatically just takes in text. So now we're no longer getting it from our DOM. Now we're actually hard coding it and is passing it to our super. And this class, instead of it will actually take our perspective matrix also as a parameter. So as we're setting up our shaders, and once the shader is all set up and ready to go and compiled and linked, we push in our perspective matrix. And on top of that, we're going to hard code our colors and add it to our uniform. So this way we're not passing in the colors either. And this function takes care of everything that we need to do for our grid. So now we go back to our HTML page, and there's going to be a lot of changes we got to do. So one of the things we got to do is put in our shaders extra. We're going to create a new global variables, grid shader and grid model. We're going to keep global shader and global model because that's going to be our test models in our future lessons. So right now we're going to want to keep the old stuff, but we're going to add in our grid because our grid is now going to be one of our standing points in our viewer. This is going to be a standard thing that's going to constantly always render in our viewer from now on. So now if we move down to line 34, we set up our shader and we set up our model, and we set it up with all our new functionality. So it's nice and quick and easy, and there's no messiness how it looked before. You can see the code is commented out as everything was set up with our test shader and our models. Creating a new model and then creating the mesh that gets pushed into it. All of that is all now fixed up as a single line of code that it's handled. And then the only thing we do is change our unrender, I think. Oh yes, right. We just rename everything into grid shader and grid model. So that's pretty much it. So now if you go back to the browser, you see that's now our grid floor. We can rotate, we can zoom in and out, we can pan around, we can do a lot of things now. We kind of have now a VR world that we can kind of explore. I hope you guys are enjoying the lesson because I'm kind of trying to go a different route with this. Where normally in a lot of lessons you kind of learn how to build cubes first. And I thought it'd be more fun if we start building kind of a world a little bit instead of cubes. Let's build a space where we could kind of traverse a little bit and walk around in, have a floor that we can see, and then we start worry about filling up our world with stuff. So that's the route I'm kind of going at. So in the next lesson, we'll finally start hitting a little bit of some 3D objects, which would probably be a quad. I'm going to look up a couple of things that might be fun to do with quads. Shader based, really. Instead of just making a quad and coloring it one color, maybe we can do something else with it that might be fun. After quads, I might deviate a little bit, do something else that might be quite interesting. I'm not actually sure if it's work. I gotta prototype it first. So yeah, that's pretty much it. So I'm really hope you're having fun and doing the things that we're doing. So if you love the video, please like and subscribe. Comment if you have any questions. Feel free to say how bad or how good I'm doing. So yeah. So thanks a lot for sticking around this long to hear me babbling on for like 21 minutes now. That's what the little recorder's telling me. So see you guys in the next lesson. Bye.